Automakers are scrapping engines and transmissions, but electric motors are still a big, bulky burden. How do you shrink them down while making them even more powerful? I found out by visiting Yasa, a motor startup founded by Tim Woolmer, a University of Oxford electrical engineering PhD. When drivers of future Mercedes models stomp the accelerator of their electric performance cars, they'll get extra oomph out of the batteries because of something that sounds straight out of Back to the Future. No, not flux capacitors, but axial flux motors.
These machines are about a factor of 10 more effective when it comes to cooling than a radial machine, so they get 10 times more heat out, which means you can push them harder, you can shrink everything again, and that just has this cycle of size down, weight down, cost down, efficiency up. So these are the four kind of mantras we really push for.
Mercedes and even Ferrari are turning to these motors to generate gobs of torque and blazing 0 to 60 times. Axial flux motors are much smaller than radial motors, the predominant type of electric motor used by Tesla and other EV makers. But they pack a more powerful punch. The differences between them has to do with their orientation and geometry. Radial motors are shaped like sausages, with rotating magnetic rotors spinning within stationary stators. They create flux radially, meaning that it's perpendicular to the axis of the rotation. Flux is what turns the wheels of your car once you press the accelerator.
Every time you hit the accelerator, we're putting hundreds of amps, in some cases thousands of amps of current through these copper coils. As you push current through the copper, this creates an electromagnet, essentially. And because we have magnets on the rotor, they create repulsive and attractive forces, which translate into torque. So electric machine is a torque transducer. It produces torque. That turns into motion, and torque times speed is power.
Axial motors are shaped more like pancakes, with the rotor and the stator made of two discs facing each other. Magnetic coils are placed on the face of the discs, creating a much larger surface area for the rotor and stator to push against each other. Flux is generated axially, meaning that it's parallel to the axis of rotation. Since these motors generate torque at a much bigger diameter, less material is needed. Yasa uses just a few kilograms of iron for its stators, reducing the mass of the machines by 80 to 85%.
And obviously we're into a transition now, adopting the technology for pure electric vehicles, where we're scaling up the technology, more torque, more power, more speed, and also efficiency improvements as well, which are super critical for electric vehicles there.
Yasa's motors are the brainchild of Tim Woolmer. Within a few years of earning his doctorate, Jaguar Land Rover made plans to use Yasa's motors in the CX-75, a hybrid electric two-seater with enough horsepower to rival the Porsche 918 Spyder, McLaren P1, and Ferrari's LaFerrari. While JLR ended up canceling their project due to financial constraints, Yasa's motors found their way into the Koenigsegg Regera hybrid hypercar, followed by the Ferrari SF90. High-end motors like Yasa's will be crucial to brands like AMG and Ferrari as they race to electrify the high-performance vehicles that earn them prestige and profits. A year ago, AMG's owner Mercedes announced it would acquire Yasa for an undisclosed sum.
I mean, again, if you look at the history of automotive, generally the auto companies have wanted to have the engine, their core technology in-house, and I guess they're seeing maybe the batteries, the motors, this is their core technology now. So they recognize the importance of having long-term differentiation in these spaces, and so they have to bring it in-house.
Whereas in the age of the internal combustion engine, quicker acceleration and higher top speeds were achieved with more engine cylinders, manufacturers will differentiate performance EVs by getting the most out of batteries with smaller, lighter, and more efficient motors. Their smaller size could allow car makers to put one motor on each wheel, which isn't feasible with radial motors. Putting a motor on each wheel, or at least one on each axle, would allow for torque vectoring, or controlling how much power motors send to each individual wheel, for improved agility. High-speed cornering might help AMG and Ferrari drivers get over the fact that they're losing the roar of their 8, 10, or 12-cylinder engines. Yasa's motors also could completely remove the need for a powertrain on the so-called skateboard underneath an EV. That would open up more space for engineers to package batteries, create more room for bigger front and rear trunks, or allow designers to experiment with new ideas with respect to aerodynamics. I'm Craig Trudell, and this is How We Move. For more stories like this, follow us on your favorite platforms.